perhaps you can say what you think have been the most important big new breakthrough ideas in the last 6 to 12 months. But one thing I did particularly want to ask you about is, which is older material, I know, which you've spoken about before, but how the Clifford algebra 2-4, which is the thing from which you kind of recover the twistor formalism, fits into the towers of, the Bott periodicity and the towers of Clifford algebras, that whole construction, and how, I mean, obviously I know the underlying ideas about the algebra of process, but how you see that, and indeed the other structures like the metaplectic group and Ham, as fitting together within that framework of the towers of Clifford algebras, also of course connected with the Heisenberg and the Dirac algebras as the much more kind of flexible and embracing replacement for the Hilbert space formalism.
Okay. Now, of course, the problem always is, where do we start in all of these things? And I wonder if we should start, first of all, with the Clifford algebra approach.
Yes.
So let me say, first of all, I got into this because I was listening to Roger Penrose in the early days, way back in the late 60s, in which he was beginning to introduce the idea of the twistors. And he would put on the board these column 4 vectors, and I would say to him, well, what's the difference between that column 4 vector and the Dirac spinner that we use? And he never gave me a clear answer that I understood. It might have been very clear, but I didn't understand it until I started looking at Clifford algebras in general. My interest in Clifford algebras had also been triggered by some of the work that David Bohm was doing, talking about process and the algebra of process, which you probably heard me talking about. And it seemed to me then that if we could see how the Clifford algebras actually functioned, then perhaps we'd get a good way of getting some mathematical, real solid mathematical background to this idea of structure process that Bohm was talking about. And it so happened that at the time I could walk across to the University College Library and I could sit in the basement, and there were all the books of collected works of Clifford himself. And I was looking through those, and I suddenly saw that he was actually motivated by the idea of activity about process, that multiplication of 2 times 6 is not simply multiplying 2 numbers together, but repeating the 3 or whatever it is I'm talking about, making it twice, doubling things. So it's an activity of doubling, or of trebling 2 or doubling 3. And
but it was the operational content, the content of the operation that he was focused on, rather than some notion of the number as an entity, as a fixed end result.
And from that, he obtained this new algebra, which was the Clifford algebra. And he didn't know about quantum mechanics per se, because this was in the 1850s, 60s. And he was looking mainly from a classical mechanical point of view, which of course is very interesting. But what I saw in those...
particularly rotations. And,
what I saw in that algebra was the formalism that eventually became the spin structure, the Pauli spin structure, and also the Dirac spin structure. And so seeing the Dirac spin structure was then saying, okay, where does Roger's work fit into this? So then I began a systematic study of this algebra, and I found it extremely interesting. The particularly interesting feature was that already in the Clifford algebra was a thing called the Clifford group. And the Clifford group was a group of automorphisms, and the automorphisms were about the covering group of the orthogonal group. So already there's something coming in here telling me that it's not the group itself where classical physics resolves, but it's the covering group which quantum mechanics seems to be exploiting.
Yes.
Now, of course, the question is how. What I went through was that there was, in fact, I'll get to the board, there was in fact, they're a tower of Clifford algebras. The general idea is this: we've got, in fact, there is a tower of Clifford algebras, and the reason why I was interested in towers of algebras was that I read Vaughan Jones's paper of the tower of von Neumann algebras.
Yes.
And that actually was linked to not polynomials that Luke Kaufman had talked
Sure.
about.
Sure.
And so there was some topological connection between the tower of algebras, von Neumann algebras. The Clifford algebra is a particular type of von Neumann algebra. So why not try and make it work with the Clifford algebras, which I was very familiar with at this stage. And so then I thought, well, okay.
Can I stop you just for a second and ask, again, for the benefit of our viewers and listeners, the definition of a tower of algebras, what is it, what are the levels, what are the stages in this tower?
Generators.
Okay, right,
Okay,
so that's the key structure
really
here.
The key thing is the generator.
Right, okay, so
we can start,
can you give a very simple example of...
let me start in the middle, as I always do, and then work both
Yes.
ways.
Yes.
Spin. This is what we're talking. This is really what we're talking about.
Yeah.
Okay. The fact that Clifford had got spin into classical physics, when we had been taught as students
Yes.
that spin was to do with quantum mechanics and nothing to do with classical physics.
Yeah, yeah.
Okay. So the spin is needs three. So I'll do the Pauli, 1, sigma 2, and sigma 3, and these are the famous Pauli spin matrices.
Right.
So there you have three generators. Multiplying them together, you generate the whole algebra, and it's non-commutative because sigma 1 times sigma 2 is not equal to sigma 2 times sigma 1. So we've got a particular example there, and so that fitted in to a Clifford algebra, which was known as C30. 30 because you've got a metric, ordinary space has 3 pluses in it.
Yeah, of course.
And no minuses.
Yeah.
So that's where the 30 comes from. And then, of course, there is the quaternions, because the quaternions were thrown around in this, and I was always taught that the quaternions were some sort of no-no, but in fact they're very interesting structures. And they turned out to be the Clifford algebra, which was C 0, 2.
2. Uh-huh.
Okay? And remember, the quaternions was what Hamilton discovered. But then there's also a Clifford algebra down the bottom here, which was C01.
Mm-hmm.
And that's just isomorphic to the complex numbers. Okay? So what I'm thinking now, so this has got 1 generator, this has got 2 generators, this has got 3 generators, and then what about 4 generators? Well, I then looked at the 4 generators. C313 was a particular interest in Lorentz symmetry, because that's just the Minkowski space that I've got. And then when I went 1 higher, 2 higher actually,
Yeah.
then I've got 1 here, which of course is C41.
Yeah, write a bit bigger if you can.
Oh, and then finally at the top here,
yeah,
can you see
yes,
that?
can just get that in.
I'm not going any higher,
No.
4, no, it's 2, 4, sorry.
2, 4, yeah.
Yeah, you'll notice this is 3 pluses.
That's the conformal Clifford algebra, isn't it?
It goes
That's
to
the
3
C2.
minuses plus 1.
Yes.
That goes to 4 minuses plus 1.
Yes.
And then this is
Which is the 2, 4.
2, 4. And that's Penrose.
That's right, and that's the conformal Clifford algebra.
And that's the conformal Clifford algebra.
Which is also where you get out the twistors.
And that's the twistors are the semi-spinners of the conformal algebra.
Right.
So the spinners, Pauli spinners, are the come from the 2-fold representation here. The 4-fold 4-column for the Dirac come out of here. In the middle here is the de Sitter,
Oh.
which I jump over because it doesn't seem to occur in quantum mechanics, but it occurs in cosmology. Lazenby is very interested in cosmology.
Well, yeah, but of course it does occur in quantum mechanics now in space because of the so-called ADSL correspondence.
Okay, you'll have to
The
educate me.
conformal anti-de Sitter duality, which these people working on the holographic principle as fixated on.
Okay, thanks.
No, well, they seem to be, yes, it's one of the things we're hearing about.
What I've got here then, you see,
is a
that's
tower.
my tower.
Yeah, that's the tower.
Okay. Okay, so then what I found was that, in fact, now the next thing, of course, is that, well, what about the wave function? Where does that fit into the algebraic approach? Because we're told in quantum mechanics the wave function is a basic thing. Which
yes, and somehow people talk about it, the ontology being the ontology of the wave function, whatever that means.
I'm sorry, I'm going to say that's a load of crap.
I say whatever that means.
So what we look at here is, does that answer how it fits in at the moment?
It shows me how the idea of the towers of algebras
and once
is
you get to this
relevant.
eightfold.
But you're relevant. So I only counted 6 stages in that construction. Maybe I'm going with there's complex numbers at the very bottom, and then
but there are probably there are things in here which I've left out.
Oh, okay. There's
something.
I'll accept that we're somewhat. So there are 2 additional stages in the construction.
I am picking particular Clifford algebras from the tower, and I'm going to them directly because the quantum physicists will recognise them immediately.
Sure, I understand. But I also understand from what you said earlier that there is this, from the point of view of the purely algebraic structure of the Clifford algebras, that there is this natural eightfold periodicity.
Yes. Well, sorry, can I then just confirm? This is taken over the reals.
Yes.
Now you can also take over the complex numbers.
Well, when you say this, what do you mean? The whole
tower. I'm
well, even though it starts with the complex numbers themselves as the basic.
Yes. Because this is isomorphic.
I see. Also isomorphic to the complex.
Isomorphic to the complex numbers. It doesn't use the complex.
No, I see. Got it. Okay. Got it.
So everything. So you can do. This is the fascinating thing when I saw how to do the Bohm's theory for the spinner, and for the Pauli and for the Dirac. Remember, the Dirac had not been done by anybody.
No.
What I found was that once I knew how to do the Pauli, and here I was inspired in some degree by Hestony's work and by Doran and Lazenby's work, but I never found them completely satisfactory for various reasons I won't go into now, they're technical reasons. So, where was I?
All of this is over the reals.
Over the reals.
All of this is over the reals. Yes.
Okay. But then you can also do this all over the complex numbers.
Right.
And then what you find is, you see, you don't have the distinction of the metric. Because you can always go to the Minkowski space, which was making time imaginary, and then the metric's always plus, 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 plus.
Yeah.
So then you've got a rather thin tower with nothing very interesting in it. But this was a tower which actually Jones had in his tower of algebras.
Of the von Neumann algebras.
Of the specialized von Neumann algebras, because and it was a type 2 von Neumann algebra. I think, I mean, please, this is off the top of my head and I might not be quite right, but it was the type 2 algebra, and that was the spinners that we use in physics. So there's always this tussle. Do we need the complex numbers, first of all? And secondly, or can we get away with the reals, or do we really need the complex numbers to make a more comprehensive structure? Because Penrose thinks we have to have
He's
complex numbers.
Very well known for his insistence.
And I think I agree with him, because we have to manufacture a complex number if you want to compare it with physics. And for instance, in this, it is the product 1, 2, 3, and that behaves like I as far as the rotations are concerned, but not as far as the inversions are concerned. So it has some of the properties of the complex numbers, but not the inversion properties.
No, no.
Okay, so that's really a sort of a,
Yes.
a physicist's way of getting into it.
Yeah, sure.
Okay, right. But this is the structure that I've mainly used because we want to distinguish between the metric, because the metric plays an important role in physics. Okay. So now then, what I was going to say was one of the, let me go to the Bohm, can I go to the Bohm theory now just to say, for the Bohm theory, what Bohm did was to say, let me take the wave function, or I've got to ask, the question I was asking, how does the wave function fit in?
Yes, that, he was just posed that question.
So what Bohm did was to simply say, let me be very naive, and h bar is always equal to 1.
Mm-hmm, mm-hmm.
Let me decompose the wave function into Rs, these are real numbers, and here is your imaginary.
Mm-hmm.
And then what you find is the Schrödinger equation becomes two equations.
Mm-hmm.
One is the imaginary part,
And the other is the real.
yeah,
Part.
and that is conservation of probability.
Mm-hmm.
And there is the real part, and that is conservation of energy. Physicists always using that, they don't like that for some reason, right? It's not as well used as the probability. But both of these are essential for a complete description of the quantum system. Okay, but now notice that what we've done here is we've used the complex numbers, so really Schrödinger equation is actually a special case of a complex, of the Clifford algebra. In other words, you can do the whole of Schrödinger's, treating it as if it is an element of a Clifford algebra.
The whole Schrödinger representation naturally lives in this, inside this construction.
In this construction.
And in fact, at the very bottom level of the construction.
Yes.
Yes, the lowest of the
Of
8.
course, but the trouble is, it's sort of,
Fold
because
through.
it is so simple,
Yeah.
you have to make certain assumptions on the way through.
Yeah.
And it's only recognized as being important when you project down. So if you think this is where the whole McCoy is going on with quantum theory, then the Schrödinger approximation is a projection to these various levels.
Yes.
Okay.
Yes. Which would be, I mean, one way of resolving the problem that Dirac raises in that paper, which you had when you were talking to Peter, and I was just glancing at, but he's wrestling back there in 1965 with this whole issue of what he calls quantum mechanics without the dead wood.
Yes.
And he's saying, well, really, we have to come in through the Heisenberg
Yes.
representation because the Schrödinger representation doesn't give us. But in fact, when one looks at it from the point of view of this much richer tower of algebraic structures, in fact,
it's almost obvious you've got to go into
you've got to go through the Schrödinger representation along the way.
Yeah.
It's not an either or.
Yeah.
The apparent.
But it's only, please note, it's only a minuscule.
Yeah. Yeah.
And this is only orthogonal, remember?
Yeah.
This is only orthogonal. So we haven't got the symplectic, which is classical physics,
No.
classical mechanics. So there's something missing, and for
Yeah.
a long time I went around asking people
Right.
for this. Okay, but let me just go on.
But when you say you've only got the orthogonal, which means talking at this lowest level of the construction.
Yeah,
the orthogonality comes in by the time you get up to the top level of the twistor theory.
It's orthogonal. Everything's orthogonal.
Everything's
Everything's orthogonal. This is rotation group.
Oh, okay.
It's
Everything.
the algebra of the rotation group.
Yeah. Okay.
Right?
Yes.
And now the reason why Schrödinger comes in here,
Yes.
but not the, because you see what's missing is symplectic.
Yes. Okay. Right.
Yeah.
Yeah.
But you say, all right, well, symplectic, but this is the reason why the complex Schrödinger comes in here, because that's doing P and Q.
Yes.
Yeah. The reason why that comes in here because there is a nice local isomorphism between SP2 and the complex numbers. Yeah.
Yeah.
So there's a very subtle connection between those two in the group theoretical structure. But that's because of the degeneracy. What happens when you go up to the Pauli?
Yes.
How do you bring in the... So that's naturally the next question. The next question is, all right, very clever, Bohm.
Yes.
You've done this, but what happens when you've got something which looks like...
The spinner.
How do you split it up into it's real and imaginary? Oh, it's
Yes.
not possible because we've got... So what do we do?
Yeah. where this is the. I'm not quite sure. This is meant to be this psi is the.
This is the Pauli spinner.
This is the Pauli. Okay, this is the Pauli spinner.
Okay.
Okay.
There, if you like.
Okay. Now I got it.
Just
okay.
to make
So that's the Pauli spinner.
That's the Pauli spinner.
That's the four component.
Okay.
The four
And the
component.
Pauli spinner then is, well, you know, we can't do this trick,
Yeah. They're splitting it into real.
the
and
real imaginary parts, because we've got an arc.
Yeah.
Okay. Now, what Bohm, Shelley and Dion, way back in the 50s recognised was, but you can express this term in terms of the Cayley
Cayley-Klein. Yes, that's right.
parameters. Okay.
Yes, right.
But the Cayley-Klein parameters can be expressed in terms of the Euler angles.
Yeah. Can you just remind me of the definition of the Cayley-Klein parameters?
Well, they are just, so what you've got here, you can represent a spinner by a 2x2 matrix of complex. So you see, here's the polar decomposition, but you can also write it as A plus IB, C plus ID. Yeah? And then so now you've got 4 parameters, and those are essentially the Cayley-Klein parameters.
Okay.
Okay? But of course you've got the Euler angles. You can the Euler angles, what have you got? You've got theta, you've got psi, and you've got phi are the usual. But if you take the density rho in, then these are the 4 parameters that specify the spinner. Okay, and what Bohm showed was that you can use these Cayley-Klein parameters, and then what you find is that this one, if you remember the rotational symmetry group, you always have an e to the I psi common to both. Okay, and the e to the I is then treated as this is the flag angle of Penrose. And then what they did was to say, let that be the action, e to the is.
So they is in this context?
Bohm,
Right, okay.
Okay.
Yes, yeah.
So then they did the same thing here by using that as a complex number, split the 2 equations out. They got a conservation of probability and a conservation of energy.
Okay.
And in both cases, you get an extra quality of energy, the quantum potential energy.
Yeah,
which
sure.
Everybody, for some reason or other,
Yes.
shies clear of.
Yeah, sure.
Whereas if you don't have it, you don't get the conservation of energy.
No.
So the question is, and what is it doing? Now, the next step, of course, would be to say, all right, we've got here for the Pauli.
Yeah.
So what happens with the Dirac?
Yeah. You can rub off if you need to,
Okay, well, I'll
because
just put
I've
it
got this in the
underneath
can.
here. So now you've got 4 of these complex numbers. And now the question is, what does that correspond to? And I have found a paper by Loschak and someone else who uses a generalization of the Euler angles for the rotation group S13. But they don't do anything with it. They just say, oh look, here are the parameters. So you've got 3 boosts and 3 rotations. And you write down the boosts as Cinch and Koch.
Koch and Cinch.
Cinch of boosts.
Yes,
So they're the
yes.
complex numbers, as it were. But they don't do anything with it. Now, what I did was to notice something which I think is very interesting. Oh, and then the spinners, the twisters rather. Are you just got a generalisation of that? I mean, it's now an eightfold.
Rather than fourfold, yes.
An 8 column,
Yes.
but you split it.
Yes.
It's something very peculiar about the conformal group, that you can split it into 2 direct sums.
Yes, which is why, as you
Which
say...
is why you get a semi-twister rather than a...
Right, which is why you said just earlier on that when talking about the way that the twisters come out of the C24, the Clifford 24,
yes,
that they actually come out as the semi...
Semi-spinners.
The semi-spinners, yes. Well, you actually said what was the expression used? They're the Well, I have to go back actually.
Okay, well,
what you
sorry,
said, but there was one particular. No, well, there was one particular thing. This was about 10, 15 minutes ago. That you said in connection with the way that the twisters appear inside the. This is when we were still in the reals in the purely orthogonal construction.
Yeah.
That they appeared.
I still haven't. I didn't get onto the point about the semi-spinner.
No, you didn't, but you did mention the one fact about the particular way that the twisters appear in this Clifford algebra, and we're staying now still with the orthogonal over the reals construction, which is different, as it were, from the way that Roger motivates them. And it's okay. I'm sorry.
Yes, it's okay. Roger motivates them from the physical idea of light rays.
Yes, of course, because
of twisting light rays.
Yes, it is.
That's it. But the point is, from the mathematical point of view, this has got nothing to do with light rays.
No, not yet.
This is just the formal structure of Clifford algebra.
Yes.
Picking out those aspects which are appropriate for quantum physics.
Yes.
And for what I want to do, of course.
Yes.
Obviously, why I'm gone in this direction.
Yes, and which, of course, is bringing in giving the deeper understanding of where the quantum potential is coming from.
Yes, and that's because of these equations.
We'll come back onto that,
we'll come back on that.
That's very important.
But you see, the interesting thing was that I was getting, from the conformal spinner, is 8 dimensions, real dimensions.
Yes.
But the interesting thing is you can factor it into 2 4-dimensional representations.
Yes, as you were saying, which you can do.
And that's the twister.
That's the twister, yeah.
Okay, and that's the interesting, that structure then became very clear to me, using this rather than Roger's way.
Is that distinction between the 2 4-component structures into which you can factor it at all connected with the way that it appears in Roger's constructions in terms of the upper and lower parts of the holomorphic plane? It is. It's the same. It's the upper and lower complex holomorphic plane.
That's the geometric
okay,
aspect.
Right. That's basically the geometric aspect of the same of this algebraic distinction.
Yeah.
Now I've got my bearings.
Okay, and also don't forget that there's this big debate about Dirac. Was he a geometer or was he an algebraist?
Maybe it was both, but I mean,
but he always emphasised the algebra.
Yes.
But then said, "But really, I'm a geometer."
Yeah.
And so there seems to be a contradiction. But there's not a contradiction actually.
It's
just 2 different ways of looking at exactly the same structure.
Yes, absolutely.
Okay, so it depends.
Which is, I think, which you might almost say is the heart of 20th century maths. That the geometry and algebra really are ultimately 2 ways.
They're 2 ways of looking at the same.
That's what Grothendieck's work is all about. But we won't go there for the moment. In my view.
Yeah. But that's my view anyway.
Yeah, okay, that's sure.
Okay.
There's old music to the choir.
So now, I want to know. So this was all the structure that I was. But then Bohm had this other idea that we want to represent not particles in classical movement in classical space-time, but we want to abstract out not only the particles, but also space-time structure
and space-time itself,
space-time structure,
the actual geometry itself. Yes.
So this is going. So you've sort of got particle physics. You've then got field theory. But Bohm wanted to go 1 stage further.
And say the space-time background itself, which is assumed, of course, in quantum field theory.
Then the question is, all right, so we want to take... I'm going back very primitive.
Sure.
So we want to take our position operator, we want to take our momentum operator, and we want to think of them as basic entities. I'll put a hat on just to just to emphasize.
You want to think of them as it were elements within this notion of the algebraic process.
Algebra of
Exactly.
process.
Rather than as being
Yeah.
Operators on the state of some particle or some system that is
for me,
itself presumes a space-time background.
Thank you.
Yeah, okay, got it.
So for me, these were Dirac's Q numbers.
Oh, don't go too high because otherwise. No, that's just visible.
Well, it's just Q numbers.
No,
Okay?
yeah, okay.
So these are Dirac Q numbers. They're elements of an algebra. Okay. But then something was missing. Okay. When I did the same thing for the orthogonal, so this is getting onto the symplectic.
Yes, yes. Yeah.
Okay.
I've got the bearings there. We're now in symplectic, and therefore.
So let me go back to. I'm sorry, you've got to go backwards
No,
and
no, no,
forwards.
no. That's the whole beauty of it. That's how things become clear. It's by jumping in the middle and working out towards both
Good,
ends.
good,
That's
Okay.
much better. Than,
So let's see. What do we do in the orthogonal case? Well, let's think of the Pauli case because it's nice 2 by 2 matrices, and everybody can multiply 2 by 2 matrices together. So we've got sigma 1, sigma 2, and sigma. So these are generators of the algebra, and I'll put hats on just to keep them company. But now, to complete the algebra, what you need is an idempotent. And that completes the algebra and defines the algebra
Yes. Yes.
completely. So we've got this, and if you look at the Clifford algebra, you find there are quite a number of idempotents. You find there are so many, you're tripping over them. So then the role was, well, first of all, why do you want to do the idempotent? Because, where's the wave function? Where's the wave function? And here Dirac already gave us a clue to do this. And I come to it, I don't know how, a slightly different way. And that was to say, well look, I can make an element of the left ideal by having any element of the algebra and banging it, what shall I call this? I'm going to call this idempotent epsilon. Okay, so my epsilon squared equals epsilon.
Yeah.
And I find this contains all the information that's in the normal wave function. So all that information is already in the algebra. So I choose my idempotent to be epsilon. Okay? Now if we go and have a look at the epsilon in its structure, what does it mean? Because it's not clear what it means. One such idempotent can be written as 1/2 1 plus sigma 3. Okay? Now if you look at that, it actually is telling you I want to break the symmetry of the structure and choose the third direction. And the way we do that physically is we define a homogeneous magnetic field in the 3 direction. And that immediately breaks the symmetry. Okay? So this is telling me that the spinor must be defined in terms of a given axis, and of course you realize that when you're doing something like that for the spinor, you're doing it in a given representation, and the representation is obtained by choosing a direction. Okay? But now we can do away with all this matrix representation, and we can say every element of the left ideal has the information of the wave function in it. So then when you get to the, just let me put in...
Just recap that again, with up to the point when you made the point about the...
So this is Pauli.
Yes.
And then of course we need Dirac, so I can go through it again.
Yes.
Very quickly. Dirac, remember
Well,
the gap...
take it as long as you like.
Gamma 1, gamma 2, oh let me not write, gamma mu, the 4 gammas. No, let me write them out just because people who are going to look at this get confused. What's obvious to me. So now we've got this, so then we need an idempotent which is going to be appropriate. I'll put a little gamma on it.
And so, of course, is everything else, including, you know,
Okay.
Joel has to.
Well, I haven't, yeah. So let's get to this.
Yeah.
And what you find here is the idempotent is equal to 1/2 1 plus gamma 4. And gamma 4 being the fourth is a time component. We're picking out a time frame.
Yeah.
So you do everything in a frame, in a rest frame.
Yes. Yes.
And then everything is, it's not manifestly covariant,
No.
but it's covariant because all you do is you do the inner morphism and you go to another frame. So it's all
Right.
consistent.
So, yes.
It's all consistent.
Yeah.
Okay, now what I am...
And of course, you need you need inner automorphism in order to have time in the
Yes.
structures, because that's exactly where the time.
Yeah, yeah.
in the-
And then the difference, so this is why time is in the algebra. Remember the Ravelli-Kohn idea? We're getting there.
Yeah.
Haven't quite got there yet, but we're
No.
getting there. Now, what I haven't done, and I apologise, is the twister should go in here, and I haven't got that in my fingertips. But people can work on it because it's just
We'll come back to it in a
straight.
little
Well,
while. And
people can
go-
work on it and just build a structure. I just haven't had time because I wanted to move on. I wanted to move on here.
Yeah. Yeah.
Okay. Oh, let me just say that when you do these, you find you get a quantum potential in each case. You get an equation which is to do with the conservation of energy, an equation which is to do with the conservation of momentum, and more. You get invariance. You construct the invariance, and these are the invariants that you can measure in the laboratory.
Yes.
And a person who's done a lot of this is a guy called Takabayashi.
Yes.
And Takabayashi, and yeah. While I mention his name, it's something important.
Yes. Sure.
Right. What you can find in the Dirac, let's stay with the Dirac because I think it's important because no one had seen how to do the bone theory in the Dirac.
No,
I've
the
done
dark
that.
representation.
Yeah, I've done that. Okay. And so what did I learn?
Very.
I learned something very interesting, that if you, from Takabayashi, that if you form bilinear invariants, in other words, you're forming bilinear objects out of here, you should be able to form, you need 8 invariants, because if you're in the reals, there are 8 parameters to specify the spinner, and you need 8 invariants in order to identify those.
Yes.
And what you find is only 7.
And even that is only giving you half of what you need for the twisters.
Then you generalise that for the twister. But then there's something interesting going on in the twisters, which I did many years ago, but I just haven't got it in mind. 7 are independent. 7 are independent. And so 1 is missing. And if you think about linear invariance, they're the things that we form by means of this sort of object.
Yeah.
Yeah. And 1 is missing. And you can see what's going to be missing. If these are, you can, there is a corresponding right ideal, elements of right ideals, which completes the picture. So if these are conjugates, you've got rid of the phase. So the information about the phase is missing. Okay? And how do you get the information about the phase? Differentiate. You bring it down. And that's what Takabayashi showed us how to do.
Okay.
You bring down, you look at invariants which are of this nature.
All right.
Notation might not be quite right
Yeah.
here because it's sometimes since I've looked at it.
And
But
then-
you have your differential, etc. And that is exactly the bone momentum coming in.
Ah.
So the reason why you've got the conservation of energy
Yeah.
is because you've got elements like that, and that's the phase, so that's going to be d by ds, and d psi by dx is in fact just the bone momentum. So the bone momentum is absolutely vitally necessary in order to complete the invariant description. Isn't that incredibly compelling?
Yes, yes.
And it
And-
hinges on that.
Yeah, it hinges on that. Is that connected at all with the way that the metaplectic group comes in as a covering? Okay,
no, it's not to do with
it's
that.
nothing to
'Cause
do
it's
with.
all in the orthogonal.
It's already
All in the
in the
orthogonal.
orthogonal picture. Okay.
Nothing to do with the symplectic.
Nothing yet to do with the symplectic.
No, not as far as I know.
So we haven't yet got to. Okay, right. So already, even in just in the orthogonal, the real space picture,
Based on the reals,
you're already getting the momentum in
as an
spectrum.
essential,
Yes.
one of the essential invariants.
Yes.
There are 4 others that you could use, and I'm afraid I haven't explored what they mean. That's up to the younger generation with bags of energy and nothing better to do. Okay?
Yeah.
But when I saw that, and when we do this, there is a quantum potential, clearly, because if you've got an invariant which depends upon the momentum, the local momentum, there's going to be a quantum potential in there, whether you like it or not.
Yeah. Yeah. Exactly.
So the quantum potential, so bone theory goes through relativistically, provided you take this lot seriously.
But yes. And the 4 invariants that you say you haven't yet, as it were, identified, where are they in this?
Have a look at Takewaya's paper.
Okay. No.
So then the next...
And how interesting. So, in fact, his motivation for this is not directly coming from quantum foundations, it's coming from hydrodynamics. Am I,
Well, in the sense
Or is it in the sense
that...
of what?
In the, no, okay.
or has he already got some? Okay,
No.
I don't know his work at all.
No. The reason for that is because when you look at the bone theory,
Yeah.
that's the one that I've rubbed out,
Yeah.
that's... who's the hydrodynamics man who started this all? Madelung.
So, again?
Madelung.
Right. Okay.
And because the continuity equation is like one of the Euler equations in hydrodynamics.
Right.
Okay, so it looks as if it's almost like hydrodynamics, but it isn't quite.
Okay.
And therefore he talks about relativistic hydrodynamics.
Okay.
In other words, making relativistic invariants of a hydrodynamical model to see if we can get some more insight into this.
Yeah.
But this is done purely by the Clifford algebra.
Right. Yes.
Okay?
Yes, I see. Anyway, it's fascinating to see that you get the Bohm momentum and the quantum potential naturally
an
appearing in this.
essential
Yes.
feature,
Yes. Yes.
not just accidental.
No, I can see.
Essential.
Yes. Yes.
Okay.
Fascinating.
Now, what does this have to do with that?
Yes.
This is the, where is the idempotent in the symplectic structure?
Yes.
Okay.
Far away.
So we've got all this now. I saw this, and I was wondering, where's this idempotent? Where is this idempotent? Now, why was I saying that? I thought that once you define the Heisenberg algebra, the
Yeah.
P and Q don't commute,
Yeah.
you've got quantum mechanics. But if you look at the Heisenberg algebra, you then look at the Heisenberg group by treating it as a Lie group, and usually they use exponential, you get the Heisenberg group.
Yeah.
And the trouble with this is it's nilpotent.
Hmm.
And if it's nilpotent, it has no idempotence in it.
Yeah. By definition.
Disaster. All my life's work has failed. Until one day I was reading Dirac's Principles of Quantum Mechanics.
Yes.
The standard book that we all study and we all should know inside out.
Yes.
And I saw on one page a symbol which looked like that. And he calls it the standard chem.
Yes.
Okay?
Yes.
And I'm looking at it and I'm saying, well, So he adds it.
Carry on.
But you can see something's wrong with it because it's a ket. It's not an element of the algebra.
Listen.
Yeah?
Yeah, I'm listening, don't worry.
But then he's also got a standard bra.
Yeah.
And now I look at that and Lou tells me in an excited way
Mm-hmm.
that if I do this,
Yes.
multiply them together,
Yes.
I get...
You've got a braid, we've got a,
No, I've got an idempotent.
yes,
Provided I put that equal to unity,
yes,
but of course I can always get rid of that if it's a Q or something else
Yes,
by
yes.
dividing.
you've got an idempotent.
So what standard, the standard bra,
Yes, yes,
standard ket, and the standard bra, when you put them together, you get the idempotent. And that is the idempotent that is missing.
but isn't there a kind of topological meaning for this construction in
I would like you to tell me what it is.
Bit Lou's,
Yes, oh yeah.
yeah.
But I can't quite
Isn't
make it work. I'd rather tell you what I work.
Okay, you tell me what you've been working with, and then we'll get
Yeah.
Lou to come in and say where he thinks this fits into his.
Right. Okay. So what we've got then, Mike.
Yeah, I'm listening. Don't worry,
Here
I'm
is the
listening
answer.
carefully. Hang on, so just give me a split second.
Yeah.
Because this camera's about to give up the ghost if I don't plug it in. But I have to be very careful because it's not.
Stable.
Yeah, you carry on.
I'm stable. Okay. Now look at that picture.
Yes,
Remember,
looking very
exactly
carefully.
the same with sigma 1, sigma 2, sigma 3. I have 3 generators there. Here, one
Yes.
got 2, and the idempotent.
Yes.
Here, the idempotent was in the algebra. So now, what I've got to do to get the symplectic Clifford algebra is I've got to introduce an idempotent into the Heisenberg algebra,
Yes.
and that's what I've been calling the extended Heisenberg algebra for the last 20 years.
Yes. 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 That's
Okay, but now I know
where it's coming
where
from.
it's coming from.
Yes. Yes.
Clearly.
Yes, because before you basically had to put in the idempotent by hand, hadn't you?
Yes.
Yeah. Yeah.
Well, I'm still putting it in my hand, but
Well-
I'm telling you what the structure is.
Yes. Yes.
Now the most important thing that happened recently. You know, I got hospitalised because I had a pancreatitis.
Yes.
And when I was going to get the secondary treatment, Glenn Dennis,
Yes.
because I mentioned his name, bought me a book.
Yeah.
And it was called Lectures in Quantum Mechanics
Mm-hmm.
by Dirac,
Mm-hmm.
with the notes by Dasgupta
Mm-hmm.
and George Sudarshan.
Yes. I know the book.
And you don't know about standard?
No,
Gauge?
I don't, because I haven't studied the book, as I should have done, of course, I'm afraid. No
So
excuses.
then, because I knew about this, perhaps I'll just backtrack a little
Yeah,
bit.
yeah, please.
I'd been introduced to some papers called Quantum Geometry by Mario Schoenberg.
Of course, yes,
And Mario Schoenberg had just this,
yes.
well, he actually was using the annihilation and creation
Yes,
operators
yes.
rather than the P and Q, but he eventually got to the P,
Yes.
and it was such a mess, I didn't know what he was talking about. They're good papers now,
Yeah,
I know what
sure,
he's talking
sure,
about.
sure. And he, of course, was David's collaborator,
Yes.
or David was his collaborator back
Well,
in the
this-
50s.
I read his
so,
work, you
yes.
see, and he had this extra, where's he getting it from? Why is it there?
Yes, why is
What
it?
justification? Is it consistent? Okay. So then I read this book while I'm waiting for something to be shoved down my throat. And I find in there that Dirac has now changed his notation. He writes the standard cat like this. Okay?
Yeah.
S standard. I should point out that Fabio Frescura and I wrote a paper way back in the 70s where we used the symbol because we knew it was isomorphic,
Yes,
the vacuum projector.
yes, yes.
So clearly
Yes.
it's to do with
Yes.
some projector onto the vacuum, but we're not projecting anything.
Yes.
It's an idempotent.
Yes. That's not your paper about the spinner, that's an earlier one.
It was in the Brazilian
Yes, I know the one you
Big
mean.
long in the Brazilian Academy, and the
That's
reviews
right.
of Brazilian
Yeah,
Academy.
yeah,
of
yeah,
Science.
yeah, I know the one you mean, yes, I've got that.
That's a brilliant paper.
Yes, I agree,
And
I agree.
It's
You-
Fabio's contribution was fabulous.
Yes, I agree. You ought to republish that on your website.
Yes.
Yeah, I agree.
Okay, so you with me?
And PDF, yeah. No, I agree, that's a beautiful paper.
Schoenberg had introduced a dagger.
Actually, can you do that under... Yes, it's a bit difficult to see over there because of the light.
All right,
Sorry about that.
no problem. Schoenberg had introduced the algebra. I use the modern notation: A dagger and V, where V was the vacuum projector. This one. And I didn't realise that the physicists had already done that. So the physicists had already extended the Heisenberg algebra without actually knowing what they'd done.
Yeah.
Okay? So that all fitted in nicely, but I didn't quite have Dirac's authority to go ahead. Then I read this book,
Yeah.
the lecture notes. And now something very interesting came on. Because what he said was, all right, let me define an algebra with Q, P, S, S, but I'm going to write a Q under there.
Yeah.
Okay? And that is X representation of the algebra.
Right.
And then he said, but wait a minute, I can also do
Yeah.
and that's the P representation.
Yeah.
So how do you distinguish between these two? This one has P, S, Q equals 0 and S.
Can you write that a little bit bigger? I'm so sorry, Baz. It's just that... It's because I can't focus this because of the
Okay, is that okay?
instability, yeah.
And
Well, yes, just, I think. Hang on.
but this one
Yeah.
is Q, S, Q equals 0.
Yeah.
So now what I can do is I've got my idempotent and I can now write my wave function as an element of the left ideal.
Hmm. Hmm. Hmm.
Bingo!
Bingo, yes, yes. So once again, you've got the wave function just dropping naturally out of the left and right ideals of...
Yes,
And,
but there's
therefore-
more.
Yeah.
Dirac goes on and says, can I do this with spin? In the lecture notes.
Yeah.
Can I do this with spin? And so what he does is he takes his sigma 3 defined in a representation.
Don't rub any of this off yet, by the way, until I've
Yeah, okay.
taken this and zoomed, because I'm not sure
Alright.
if this will come out on the
And then he
existing-
says, let me define my standard x-ket by means of sigma 1 equals s. Can you see that? I'm sorry, I've...
Not very well. Can you rewrite it a bit bigger? Or yeah, I think that should be okay. Yeah.
And then what he shows, I'm not going to go through the proof, and then he shows that the standard ket is 1 over root 2, 1, 1. Okay?
Yeah. Yeah. That's
Now,
beautiful.
we've already seen what the Clifford algebra.
Yeah. Yeah.
Okay? So what this would be So now I've got an idempotent,
Yeah.
okay? So the idempotent, Sx, Sx. How do I write that? Well, if you multiply this out, it's just 1/2, 1, 1, 1, 1. Okay, because you're doing a tensor product,
Yeah.
not a scalar product between the two. Okay? So that, well, you can work at that. Yeah?
Yeah.
You look
Yes.
puzzled, but I'm sure you
No. I'm just
now I
slightly
say
worried
to
about
myself,
how
"Oh,
clear
that's
this is going to
interesting."
show up.
That's interesting. Because if I take my 1/2, I take my idempotent 1/2, 1 plus sigma x. Remember I had sigma z before?
Yes.
So
yes.
I'm taking the idempotent which defines my x-axis.
Yes.
I find that's equal to 1/2, 1, 1, 1, 1. Isn't that beautiful?
Yes.
Huh? So we're talking about the same thing. We now know what this
Well,
standard ket is.
Yes. Yes, it's absolutely fascinating to see just how very naturally and
The whole thing falls out.
falls
yeah.
out from
And Dirac
thinking.
was doing this in the 20s
Yes.
and the 30s. And it was just ignored because it didn't fit in with
Well-
Bohr's philosophy.
And it didn't fit in with Hilbert space.
No, because Hilbert space is not the essence.
No, exactly. As he had actually already seen intuitively back
Yes,
then.
of course he had, because he had that paper, remember, which we were looking at over coffee just now.
Yeah, well, that was written later, and that was in the 60s.
Yeah, but it takes
But
time.
yeah,
takes
sure.
time.
No, I'm not saying he.
And that's-
yeah.
Quantum electrodynamics was acted towards.
Yeah.
And that's where he actually says, I want to say it on tape,
It's very important.
is that if you use the Heisenberg, and I'll come to it in a minute, the Heisenberg representation,
Yes.
the standard ket cannot be put into Hilbert space.
Yes.
Cannot be put into Hilbert
Yeah.
space. And therefore, he's saying we've got something which is more general than
Yes,
that,
yes.
and I don't know what to do with it.
Yeah. But now you can really see where
Now
it's
you
coming
can see
from.
where it's all coming from.
Yes. And of course, above all, it's coming from this underlying interrelationship between the minimal left and right ideals,
Yes,
which is giving you in turn the idempotence, the non-trivial idempotence in the
also
algebra, and of course explaining in what sense. I mean, further going deeper into the kind of intuitive and, dare I say it, kind of metaphysical payoff of all this, where the algebra itself is what the meaning of this in the entire algebraic structure is, which is essentially to do with an unfolding and enfolding
these
process.
are not elements in space and time.
No.
This
There's
is
some
totally
kind of
independent of space and time.
Well,
But they encapsulate the symplectic structure
yes.
and the orthogonal structure.
And in fact, they indirectly kind of giving you the space-time background.
And somehow the
In a
space-time
sense,
background is
is
encoded
Is encoded inside this.
inside the space.
Yes.
So what we're really beginning to get our hands on is a quantum geometry, a non-commutative geometry.
A non-commutative pre-geometry, perhaps, would perhaps be a better way of saying it. Which is exactly what we were talking about in Leipzig with these guys.
Yeah.
But they don't know this work, that's the problem.
Yeah.
So they're coming from various approaches
And I'm sure
to
they've
do
got lots of
with,
contributors to-
sure, like this quantum Riemannian geometry and other ideas, and of course Cohn's approach, which is essentially coming out of spectral structure. But again, the point that they were all stressing is that it's the non-commutative structure that is really basic, that is ontologically basic. Yeah, I know, and of course I don't worry. And I was saying, well, you know, there is this group of guys who've been saying this now for 40, 50 years, and who got it in discussion with people like David Bohm and Roger Penrose back in, as I say, 50 years ago now, in Birkbeck and six, and nobody's been listening. And now here are all you guys coming and saying, well, picking up on, I wouldn't say anything to discourage them, picking up on small pieces of aspects of this picture, coming from different
But isn't
angles.
it
Well,
so
you really,
beautiful?
really do need to get
Don't you
together.
think this story is beautiful?
Yes, I really do. I seriously, I'm not saying
I mean,
that to be
I
polite.
don't claim any.
It's stunning, and I just cannot get why it is that people have not been listening, except that it is a very strong sense I have now listening to these people in Leipzig, that there are a lot of the younger people out there, particularly on the algebraic side, who have been looking at.
They've got rid of
Hamilton.
the old men who think you.
Yes, that you can't think without
can't
Hilbert
think
space,
about
or yeah.
these-
And they're intrigued by all the new structures which are coming into theoretical physics anyway, including from quantum topology.
I've got two directions I could go in.
Yeah, go ahead.
Right? One's going backwards, and the other one will be going forwards. Now I just go down as far as here.
Yes, okay.
Okay. So now we see the structure. But now, why did Dirac introduce the standard Ket? Because he said, I don't understand why we can't work totally in terms of quantum variables. If you look at the classical Poisson bracket structure,
Yes.
you look at the quantum structure, there seems to be an analog between the Poisson brackets and the commutators.
Which is where the whole theory of deformation quantization is coming from.
Yeah.
Yeah.
What put the blocks on that approach was because people directly changed Poisson bracket into the commutator. Directly. And then there was the Van Hove-Grunwald no-go theorem, which says once you got to, I think it's cubic powers, it doesn't work. There is no isomorphism between the structures as such. But Dirac was not put off by that. What Dirac was saying is, all right, so I think it's clearer if we say he was working towards Q numbers. And he said, why do we, look, when we're working with the operators, so we've got an psi of the operators and we operate on this thing, what this tells me is that I mustn't multiply by anything on this side. So what he was doing was constructing a left ideal.
Yeah.
But he didn't say that's what he was doing. So you don't need any parameters, any eigenvalues. The structure is in the operators themselves, but we're not thinking them as operators, we're thinking them as Q numbers,
Yes.
which are part of the algebra.
Yes.
And this is the algebra of process that David Barr.
They're not elements coming from the outside operating on states of some
Right,
already
they
given
are
thing. They are internal to the algebra itself,
Absolutely.
because the algebra is itself to be understood in terms of self kind of subsistence structuring activity.
Thank you.
Yeah, thank you.
Yeah, that's what I've been
What the
trying to-
metaphysicians call an absolute process monism.
Yeah, he calls it the dynamics of a wave packet. And he says, let me write psi of r and t as a e to the I s.
Oh, hang on, you're going too high. I'm
Oh,
sorry.
too high?
Yeah, can you just do that again, but a little bit
Okay,
lower
fine.
down?
I
Just
won't put a detail.
six
Just-
inches lower down. Yes, that's perfect.
Psi
As big as you can make it.
equals a e to the I s.
Yes, that's better. Yeah.
Oh, we've seen that before somewhere.
Yes.
And then he says, now I want to write that algebraically. I want to take Schrödinger's equation, I d by dt of a e to the is. Sorry, just let me get it.
Don't worry,
absolutely
don't worry.
right.
No, take it.
Yeah, hold on, that's right.
Don't worry. It's great that you're firing on all cylinders like that.
Is equals h
Try to keep the writing as big as you can.
p a e to the I s In other words, he's expressing it all in terms, perhaps I ought to put capital Q and capital P here, because he uses a very difficult notation. So let me be consistent, capital Q, capital P, or capital P. Okay?
Yeah, yeah,
So everything, this is just a Schrodinger equation.
yeah.
And then what he does, believe it or believe it not, is he differentiates out, and he then separates into the real and imaginary parts. Okay?
Yeah. Just as you were
But-
showing is needed in the treatment of the Schrodinger
Yeah,
equation in the clevered algebra approach. Yeah.
Yeah. Yeah, exactly. So he's done the Bohm theory.
Yeah.
Yeah.
Yes.
What he shows is that e to the I, that's minus, s, I've got h bar is equal to 1 again, p, capital P, e to the I, s, is equal to p plus ds by dq. And these are operators. Oh, God. Sorry, I'm translating.
Yeah. Yeah.
So we've got the Bohm momentum coming in already. It's an additional term that we add to the operator. And then we show that e to the minus is of h q p e to the is is equal to h of the q p plus ds by dq. Okay?
Mm-hmm. Mm-hmm.
And then he puts that back into the Schrodinger equation and separates real and imaginary parts.
Why
Huh?
is this not better known?
So you see why I went to the book to
Yeah,
look.
yeah.
It's doing what we've been doing for years.
Yes, yes.
And then we get the Bohm momentum coming in.
Yeah.
And what you find is the Bohm equation for the conservation of probability,
Mm-hmm.
cons of prob. And he talks about it being a hydrodynamical model.
Really?
Yes. Doesn't mention Madelung.
No.
Can I read you his actual words?
Well, conceivably, this was written before Madeline's.
No!
No.
This is 47 edition.
Well, okay, I'm sorry, I don't know the dates. Madeline is a new name to me. Madeline was writing what,
Madelung
when?
1925.
Oh, okay, okay. Sorry,
Sorry, I'm not- just-
sorry, but I haven't got a
just because
fix
I
on
shout,
the.
I'm not
No,
gonna
I know you're not. Don't worry.
Right.
I realise that. No, it's because you're excited by this, and so am I. No, I hadn't realised that Madeline had. As I say, his name was entirely new to me, so I hadn't realised that he'd done this stuff.
Yeah, and then let me
90
say,
years ago.
Okay. Yeah. And then what he gets. But notice this is all in operators.
Yeah.
These are all operators.
Yes. Yeah.
What Bohm did was to write it all in terms of ordinaries. Yeah, because his X's and P's and Q's were all just ordinary X's and P's and Q's.
As in the Hamilton.
As in the Hamilton-Jacobi.
Jacobi, exactly.
So he got, but Dirac got H, J to order. He went to the order
Of
H
H
bar. This is the order of H bar. He didn't go any higher. He threw away all terms of H bar squared.
Ah.
And the quantum potential comes in for the first time, H bar squared.
At H bar squared.
So he threw it away.
Yes.
And he said, oh look, we've got the classical Hamilton-Jacobi equation,
Which he had.
which he had. Leaving H bar in, he had to do it for the probability equation,
Yes.
because it has, because the Moyal bracket has an H bar underneath it just to tempt you.
Yes, about the point about the Moyal product, the Moyal bracket,
The Moyal bracket.
the Moyal
And that's where
quantization essentially
deformation-
already having got the quantum potential
That's where
inside
the
it. Yeah.
deformation comes out. Now somewhere he says this is like, I'm just trying to find it, it's like a hydrogen. Yeah, here we are. To get an understanding of the significance, of its significance, that's the first equation, the conservation of probability.
Yeah.
Get an understanding of its significance, let us suppose we have a fluid moving in space of the variables q and the density of the fluid at any time, point and time being a squared, a capital A squared, that's r squared in Bohm's language. The velocity being dq by dt is that. The motion, equation 42 is then just the equation of conservation of such a fluid. The motion of the fluid is determined by the function of S satisfying another equation, there being one possible motion for each solution of the wave function. That's just Bohm.
Does he have the conservation of energy in there as well?
No, what he says there,
What does he say about that?
he tries to justify why he's throwing away terms of h bar squared
Yes.
and above.
What does he say about that?
Or just about something being, I'm only considering terms where so-and-so is greater than something and less than something, and it's equivalent to throwing away h bar squared.
Yes, yes.
So why be clever when you can just say... And then he says, oh, come on, boy. And he then says that a more accurate solution of the wave equation, one can show that the accuracy with which the coordinates and momentum simultaneously have numerical values cannot remain permanently as favourable as the limit allowed by Heisenberg's principle of uncertainty. So
I don't quite understand what he means by that. We cannot permanently remain as favourable. What do you mean, that you can't get? You can't get any tighter bounds on the non-commutativity? Or
I interpret that as saying,
I
I said I had to, because I wanted to quote from Dirac, and it's not coming from BJ or anybody else.
No.
Yeah.
No.
I think he's saying that if I allow terms greater than q squared,
Yes.
I'm going to run into trouble with the Heisenberg uncertainty principle. And so he abandoned it.
Yeah.
Now, don't mind if I sit down.
Yeah, of course not. Yeah.
As I began to read somebody else who I've just introduced, Moyal's work.
Yes.
And Moyal is in 49.
Yes.
This is 47. And Moyal goes to Dirac and starts having a discussion with him. And Dirac says you can't do what you're doing. Because what Moyal wanted to do was to have functions, not of operators, but of C numbers.
Yeah.
Okay?
Yeah.
And what Moyal showed was that if you can generate a non-commutative algebra, I come down here.
Yeah. Fine. Okay. That's all in the can.
So these are ordinary phase space, classical phase space,
Yeah.
ordinary functions, infinitely differentiable functions.
Yeah.
In order to get quantum mechanics out, you have to introduce a new product. Just a star product. This is the Moyal star product.
Yeah.
And the point is that star product is non-commutative.
Sure. It has to be. Otherwise, you wouldn't get quantum mechanics out.
Yeah.
Okay.
And then he shows what form it should take.
Yeah.
And if you look at it and go to the limit, neglecting higher order terms h bar than h bar, you get the Poisson brackets out.
Yeah. So thus showing that you don't have to, as it were, go straight from the Poisson brackets to the commutator in this picture. Rather you can...
Yeah, he was working on generalized statistics, quantum statistical theory. He came in from the school, how do you generalize classical statistics
Yes.
in order to get quantum mechanics.
Yeah, this is Moyle.
This is Moyle.
Yeah, sure. Okay.
Dirac was going the other way.
Yeah, yes.
He said, I'm starting with the algebra that Heisenberg has given me, this is 1926 I'm talking about now. And then he shows how the rules that Heisenberg started to get eventually give you the commutation relation between Q and P.
Yeah.
So there is, what they've shown between them, and I'm sure you can do this formally, any mathematician can do it, is that the Moyle structure is isomorphic to the quantum algebra. So whatever you can do here,
Yeah.
you can do here.
You can do on that side. Yes.
And whatever you can do here, you can do on that side. And that is the summary of deformation quantum mechanics.
Yeah. Yes. Exactly.
But
But of course, the way that Moyle is introducing it, because as you say, he's coming from statistics, from classical to quantum statistics. He's thinking of. So he starts with a space of differential forms essentially, well, differentiable operators.
Yeah,
that's,
differentiable objects.
Differentiable objects, yes. And then as it were, shows how by purely algebraic condition
you
can
theory of
get
moments.
them.
In classical
I don't know the first thing about statistics.
you have a theory of you develop characteristic functions and moments and so on.
And this is where the non-commutativity is coming
And
from.
he does that in terms of operators.
Right. And that is how you get the
And that's
non-commutativity
how you
out
get
of the Moyle
Yes.
product. The Moyle, okay, the Moyle. Okay, right.
Yeah, okay.
So
But-
that's where you put the bounds on the, and I can see. So I can see from that why Dirac is, wants to throw away the terms of h bar squared or h bar to
H bar squared.
h bar
and
squared or
higher.
above, yeah, because that would you can see that would give you some kind of the idea was that you would no longer have any. There wouldn't be this kind of fundamental obstruction to that comes out of the non-commutativity to the difference, which is what the Heisenberg uncertainty principle, which would violate the Heisenberg uncertainty
It's rather
principle.
interesting that what Morris and I did was to show that if you only go to the order of h bar, we were doing Zeno's paradox, and Zeno's paradox holds.
Yeah.
It's not until you allow the quantum potential to develop
That you get
go to h bar squared and higher, that you get
the so-called quantum Zeno effect.
Yes.
Yeah.
So in other words, at one level we've got classical physics. We're doing something trivial now, I come to think of it, but it seemed to be very important because we came through it a totally different way.
Yeah.
We came through it through the covering group of the symplectic group.
Yes, which is the metaplectic group.
Which is the metaplectic group.
And all of that business about the so-called metaplectron that is Morris's way of expressing it is just a kind of, a way of saying in terms of these higher geometrical structures what is going on, what Moyle was motivating really from statistics, from classical statistics, or rather from the kind of obstruction that prevents prevents quantum. The quantum formalism from recovering classical statistics because of the Heisenberg uncertainty principle. Yeah, I've got that.
Okay.
Yes, no, it's very, very
now, what I've now shown in the paper I've just put on the archive is that the Bohm theory, in fact, is another picture, and I call it the Dirac-Bohm picture because of this background.
Yes.
And because the transformation we use for the Stone-von Neumann theorem is that. Remember, the Heisenberg uses e to the I h for your unitary transformation.
Yeah.
But if you use e to the I s, where s is the classical action, you get the Dirac-Bohm picture.
Very interesting. And you said that there were two other ways of coming at this, and you've just dealt with one.
No.
So what was the second last one?
One other.
Or two others, and one other you wouldn't want to talk about.
one other.
And then I want to ask you just a little bit more about how the Moyle picture, how the quantum potential is already inside the Moyle.
Okay, you want me to do the Moyle picture?
Well, if you want to give me the Moyle picture that it explains your discovery, if you like, your insight that the quantum potential is already in Moyle's 1949.
Oh, that's in the appendix. That's in the appendix.
Okay, well, run it past me again. That
That's
would be
in the
interesting.
You're so
Yeah.
squeezing me out, aren't
Yeah,
you?
well,
Can I just say one thing before I get on to that?
Of course.
And that is that this Moyle product was actually introduced by von Neumann.
Uh-huh.
In 1931. Now this to me was staggering
Yes.
because von Neumann just publishes his book
Yes.
on the mathematical foundations,
Yes.
and in there is all Hilbert spaces.
Yes. Yes. Of course. Yes.
And then he comes up in 1931
Yeah.
with a purely algebraic
Yes.
approach. And nobody seems to have realised.
To notice that he is completely.
He's now standing on his head.
Yes. Yes.
And then I learnt from someone, I forget who it was now, that his book was actually the lecture notes of Hilbert. So he'd actually polished up and put his own interpretation on what Hilbert was lecturing on. Second point, I heard from David Finkelstein that he didn't write the last chapter in the book on Foundations of Quantum Mechanics.
Von Neumann did.
Von Neumann didn't.
No, really?
It
Who
was
did?
written by Widner.
Oh,
And that's why you see consciousness creeping in.
how very interesting. Never knew that.
And I heard this, David and I were at a conference, a young lady who came in with a cameraman for some other film.
How I wish we could have got that in there. How I wish, of course, if it hadn't been for these 5 years of delay with
Yeah.
we could have done a couple of more interviews with David before it was too late.
Yeah, he was sick, yeah. Anyway,
It was wonderful.
he said this in the discussion, and I'm
Yeah.
always very worried that I never pick up the right message.
Yeah.
So I was having a cup of coffee, and I went up to him and I said, "Tell me, David, did you say Widner wrote the last chapter of von Neumann's book,
1930 book, yeah.
30?" And he said, "Yes, I said that because Widner told me."
Yeah. Well,
So that was always a mystery. It seemed to
Very
me that
interesting.
the style changed at
Yeah.
that last chapter.
it clearly, obviously did, and now we know precisely why. I must
Okay.
talk to Guido Bacigalupi about that, because I'm not sure if the historians of physics know that. Maybe some of them do. Anyway, let's not go off at that tangent.
When there's one other thing that was coming up then.
Why it was that in 1931 von Neumann went to this
but
strikingly
then-
algebraic alternative
Then immediately after that, just
presentation.
let me complete the history.
Sure, yeah,
He
yeah.
went with Birkhoff
Yes,
to talk about the logic of quantum mechanics,
yes,
because he was basing on the idempotence.
yes.
And also to notice that this paper is the paper which with Stone becomes the von Neumann Stone paper. And that was that the Schrödinger representation is unique up to an automorphism, a unitary automorphism. And what we've been playing around with in these algebras is we've been playing around with pictures, and pictures are different automorphisms of the quantum algebras. And a lot of people don't seem to appreciate that. So now you see everybody basing it on the Schrödinger picture. What about all these other pictures?
Yes, what about other-
where do they come in?
Yes. And how are all these automorphisms related? Then are they inner automorphisms of some
I don't know.
single overarching algebraic structure, or is
Over the coffee table just before we came over here,
yeah,
there was this problem. What does it actually mean
yes,
when you have an automorphism in the Fock space?
yes,
You then define number operators in the Fock space. What is the number operator in the Schrödinger space?
yes, yes. What's the notion of it?
Okay, and so these problems are still there.
Yes. Of course, even when you define the number operator in the Fock space, in the Fock representation, it then of course becomes itself a quantum variable.
Yeah.
So of course,
you create algebra. You create a richer algebra by doing that.
Yeah. But you also, of course, cause the most profound, conceptual problems, or raise the most profound conceptual issues for our understanding, I would say, of the notion of a cardinal number as the number of a set of objects taken in extension.
Yeah.
There's something wrong with that notion, because
this is, in a way, like cardinality.
Yes, except
because you're putting more and more particles in there.
Yes, but then what does, from the point of view of even of the Fox representation, what does the notion of more and more has become ambiguous, hasn't it?
Yeah.
So there's something.
Somehow more and more. You see, to me it seems that you've got the conservation of energy in the Schrödinger picture.
Yes.
So what you must be doing, if it's isomorphic, is that when you get more and more particles, you keep the total energy the same, but the energy is distributed.
Well, that would be one
in
obvious.
a different way.
Yes. Yeah.
That's the way I'm looking at it at the moment.
But of course, it may be that not in such a way as that conserves, occupation number, the value of the number operator in any particular representation.
There's still some question marks.
Yeah, there are some very, very interesting issues there, which I think also connect with issues and foundations of set theory. But that's to go off at much too far at a tangent. You said that there were two further approaches. We've just spoken about one. Or two further, yeah. What was the second? And then the last thing I want to ask is a bit more about how the quantum potential comes out in the Moyle.
No, I want to do that now.
Okay, let's do that first then.
Do that now.
So the Moyle interpretation and the quantum potential.
Yeah. Okay.
Cover that.
So, what intrigued me about Moyle was many things, was, first of all, that it's the beginning of, for me, as my personal experience, the beginning of deformation quantum mechanics.
Yeah.
Because he introduces
Yes.
a Moyle bracket.
Yes.
And the Moyle bracket is defined as, in terms of derivatives, isn't it? It's essentially the Poisson bracket, so it's going to be dq dp minus dp dq on a times b over h1. And there might even be an I in there. Yes, there is an I in there. Okay? And you can see where that comes from, the Poisson bracket.
Yes.
Because that's just a Poisson bracket if you don't take any higher order terms. Okay? So that then generalizes to the commutator.
Yeah.
And this is what Dirac shows in his paper in 1926.
Yes. Ignoring the sort of kind of no-go theorem that we talked about earlier.
There was no no-go theorem then, you see. He was working from scratch.
Yeah, yeah.
Okay.
But there was this view, as you explained, that going from the Poisson bracket directly to the commutators meant that you had to impose this kind of cut-off limitation.
Yeah.
But it turns out that's not in the deformation quantization picture.
So in fact, let's call this
a
thing
problem at all. So.
D
Right.
QP. Okay.
Right.
Then, when you look at the Moyle structure, you find that the Moyle structure.
Oh, hang on, we're going too high up the. Oh yes, okay.
No, I'm coming down.
That's all right. Coming down now. Yes, so we can
Is
just
equal to,
get that in. Yeah.
F. I write in. What I should really do is to write this. Let me just tidy this up.
Yes, okay, that's fine.
Let me. The trouble is, I've come too close. Moyle bracket.
Keep the writing as big as you can because, as I say, I can't
So
zoom.
this is A of QP.
Yeah, I hope that's going to be visible.
B Well, anybody with any intelligence.
Yeah, can realise what you're saying.
Sorry, I'm being rude again, I presume. Okay, so then we have f d of exponential, sorry. And please, there might be some mistakes in this for those finicky people who like to have everything dead right. H bar D Q and P. So you always have a government health warning whenever I talk. But the whole point is to get the idea across, and then in the quiet of your home you can get all the details correct. So this is the Moyal product, right?
Right.
It's exponential. So that quite clearly means we've got an f cos g plus an I f sine g. Okay, where this is the d.
Yeah.
Yep, okay, got it. Right, so the reason why the Moyal bracket has the I in it is because it comes from the sine.
Right. Right.
Difference in the exponentials.
Got it.
This one is what is known as the Baker bracket.
Ah, yes. Our old friend, I remember the Baker bracket.
And the Baker bracket says f g star product gf probably a half. Is that object there?
Right.
Now, that happens to be a Jordan product.
Yes. And can you remind me what Baker's motivation was in introducing his bracket, the Baker bracket? What the context of the introduction of the Baker bracket was?
Very interesting. What he showed was that when you go to the Green's function approach, the Feynman propagator approach, the existence of that in his hands led him to believe, or to prove that all kernels are degenerate. Yes, sir. Yeah, all kernels are degenerate. Once you prove that,
Yes.
you then show that the wave function exists. Because the kernel for a degenerate
Oh, I see.
can always be written as a psi star of psi. Yeah?
So you've got a kind of purely algebraic rationale for the existence of the wave function.
Yes.
Yeah. Which, of course, coming at this just as it were purely just from the pure algebra, the structure is mathematically already very interesting.
Yeah.
But of course, it's suggestive of some much more fundamental, let's say, physical reason why.
Okay. So now this means
The wave function is not the place to start. It's not the.
look,
It's not the all-in-all. It's
we're dealing with a bimodule.
yes.
Okay?
Yes.
We're dealing with a bimodule.
Yes.
And that's where this all comes in now.
Yes. So okay. So in fact, the bimodule structure is there in the Moyal product.
Yes.
Right. Okay.
And the whole thing, when we come to we're put a bimodule. E is a bimodule. I think so.
That's right.
Yeah.
Yes.
So that bimodule means that we've got a vector space and we've got operators from this side and we've got operators from this side.
Yeah. Of course. Yes.
Okay. Now then, if you're dealing with a bimodule and you don't want to deal with it, and now of course we're going to come into the modern theory of Morita equivalence and blah blah, all that abstract stuff.
Yeah.
But
Sure.
it's coming from essentially because quantum mechanics is about a bimodule.
Yeah.
What we've done with the Schrödinger representation, we've turned it into a left module. because we have our operators A operating on the wave function equals something. So we turn a bimodule, and we do it by changing P into d by dx. Yeah? So the P operating that way is d by dx operating that, with an I, of course. So we turn it into a bimodule. Sorry, into a symbol. So what, if you're now basing everything on the Schrödinger equation and the Schrödinger picture, you've lost the bimodule structure of the underlying process. Why are they being so stupid and not realizing this is going on? You build a model of reality on something which is just a little ripple on the top of this deep structure. And no wonder you get into all sorts of nonsense with lots of different interpretations.
Yeah, sure.
Okay. Now, why am I'm down here? Oh, okay. So how do you deal with a bimodule? Well, essentially what you've got is operators which operate from the left and the right. And now the question is, how the hell do you deal with that if you want to make them into a one-sided module? Well, the easiest way is to form sums and differences.
Yeah, exactly. So that you recover something which behaves like, dare I say, the R arrow circling back into the point, the self, as it were.
Yeah, yeah.
Well, we need a term for it, but the arrow. No, the arrow that's on the first page of Bill's book, which we were talking about earlier, as it were, the way that one should think about what it is that gives you recovers the notion of a point in terms of activity, rather than a primitive thisness or something.
So now,
thought of this.
But now, suppose we're looking at equations of motion. We've now got H, the operator, operating on these. I'll just take the F's. Yeah. So that's going to give me something, and then we've also got to have the other way around. So our equations of motion are going to be made out of a sum and a difference.
Yeah.
And the difference, I forget which way around it is, but essential point is one of them gives you the Bohm probability, the conservation probability equation, and the other one gives you
the conservation of
Hamilton-Jacobi.
the Hamilton-Jacobi, yes. Yeah. Which, of course, is also where you get the quantum potential coming in.
Yeah. And then finally, just for, I really had enough now, Mike, sorry.
Okay, John. Well, you did say there was one, there were
that,
two things.
The second one is when you now go to the fully fledged non-commutative geometry.
Right.
And you bring con into it. To get the Bohm momentum,
yes,
what Moyal does is defines a marginal P, F of, so this F of P and Q here is the Wigner function, I'll put a W, is the Wigner function. I hope it's right.
Right.
Okay?
Yes.
And
That's a P at the end.
Here is
No, at the very end.
that's a DP.
That's DP, yes, that's
Because
what
we've got to find, this is going to be a function of Q.
Yeah, no.
A local momentum.
Yes, that's going to be a local momentum.
So the local momentum is the mean value, or the marginal,
Right.
over the non-commutative Wigner function.
Right, okay, yeah.
Forward derivative,
Yes,
that's a backward derivative.
yes,
If you make the sum, it's the mean derivative.
yes,
And if
exactly.
you make the difference, it's the osmotic derivative.
Ah, that's what it is, okay. So, which of course connects with the hydrodynamic aspect.
That's the hydrodynamic.
But how do you think that? But you were saying that there's a deeper way of understanding the path integral approach.
Because as you probe down into you want to connect 2 points.
Yes, exactly.
Here's the point X. We've got a point X here, we've got another point X prime here. Okay? And now we're working in the Moyal structure, so we've got X and there's a T implicit in here as well, of course. Yeah?
Yes.
So now how do we get from here to here?
Yes.
Okay? Well, this is information coming from the past,
Yes.
and this is information going to the future.
Yes.
And therefore what you're saying is that the mean is the sum of the two forward and backwards. And that's the local object, but this thing which is this way and that way, you can put it over 2 as well, is the osmotic. This is the local, and this is localizing.
Yes, localizing is the point, because you've got time already in the algebra as an algebraic pure process, but you've obviously also got to have a time as the parameter of local motion.
Yeah. And localizing is in terms of delta t, if you like, in my paper on the theory of moments.
Yeah, that's very important indeed, because one of the big we spent a whole day on how does time fit into the formalism, into the various approaches to quantum gravity in this Leipzig meeting, and I thought that the one, it's a very deep question, and the missing part of the picture was precisely the insights that are coming from your approach, from the algebra process approach, which I so wanted to talk to them about. Thank you so much for your patience. I do.